This week, we're going to continue learning about chemical reactions. And so we've worked on balancing equations, and we've worked on predicting the amount of products that'll actually form. And now we're going to look at what we call reaction dynamics. And so that's going to be how fast a reaction takes place, how much energy it gives off, or how much it needs to absorb to happen. And also we'll talk about reversible reactions, which is actually most reactions, and what equilibrium is and how we can affect it. And so that's kind of our big picture. And I wanted to just give kind of a concept map overview that's short of what you're going to be working on this week. I find these kind of overviews helpful for me before I actually dive into the details on something, so I kind of have the big picture. So we're continuing to talk about reactions. And within this, we're going to think about this in two ways. We're going to think first about rates of reactions. And this is going to kind of follow from this idea that all reactants form products. But really, it's how long, what a rate of a reaction is how much time passes before we stop seeing a change. Stop. All right, thank you. School's out this week. So in the case of a reaction that's going all the way to completion, then it's going to be. So when we're looking at a reaction being done, we'll either see all the products and no more reactants, or we'll have reached equilibrium. And that's going to be kind of the other thing that we're going to talk about in this week. But let's stick with rates. So one of the things that we're going to go through in this is just thinking through how a reaction actually takes. Actually, let's do it like this. When we think about rates, when we think about how fast they're going to go, there's a few things that are going to affect them. So if a reaction has increase in temperature, or an increase in concentration of the reactants, or we add a catalyst, then all of these things are going to speed up how fast the reaction happens. So the why of the temperature increasing and the reactants, all of this kind of increasing the rate, really depends on what is happening in a reaction. And so when a reaction takes place, we have two molecules that collide. And if they have enough energy, like kinetic energy combined, to overcome the potential energy of like breaking bonds and reforming new ones, if they do, then they're going to become something new. And if they don't, then they're going to separate. And so it's just a bunch of collisions. And so that means more collisions will happen if the temperature increases, because the particles are going to be moving faster. So temperature is proportional to kinetic energy. Kinetic energy is just motion. So as we increase temperature, everything's going to zip around faster. So as temperature goes up, each particle moves faster. And this is actually called collision theory. The other thing that can increase the number of collisions is if the concentration increases. It's just going to be more crowded, and so there'll be more collisions. And if you add a catalyst, this changes your reaction pathway, essentially. It's kind of like putting someone in to like grab one reactant and the other reactant and bring them together. We can characterize this process with reaction diagrams. So a reaction diagram is going to look at what happens from reactants to products, and we put it on what we call a reaction coordinate, which is not the most helpful. You can kind of think of it as time, but it's not really. And then energy, which is really going to be a measure of like the potential energy of everything. And so we have our reactants at some energy, and we'll usually just look at this relative reactants to products. And so we don't normally quantify it too much, but we can also, like, these have the potential energy of 100 kilojoules per mole. And we would put that on that part of the energy scale. And then we would have products. And for the reactants to form the products, they're going to have to overcome some sort of transition state where everything has half broken and half formed bonds. And this difference right here in energy is what we call the activation energy. Now, in this one I drew, the products are at a lower energy than the reactants. And that's going to get us to this idea of if something releases energy or absorbs energy for a reaction to take place. If the products of a reaction are lower than the in energy than the reactants, then it's going to release energy as heat to form the products. It's going to have more energy than it needs, so it's going to get rid of some of it as heat. And we would call this enthalpy right here, this energy difference. In this case, it's going to be negative because the products are less than the reactants. And we have a word for this. It's called exothermic. There's a version of this too where you would form a product that's higher in energy. And so that would look like this. Here's our reactants and our products. Still have to overcome a transition state energy barrier. So I've got my activation energy. And then here, my enthalpy is positive because the products are at a higher energy. And so we call this endothermic. And it means that you have to absorb some heat for the reaction to take place. And in these cases, the products here are less stable than the reactants when they're at a higher energy, and they're more stable if they're lower in energy. And so that gets us to this idea of endothermic reactions versus exothermic reactions. Exothermic reactions release heat and endothermic reactions absorb it. And there's like lots of exothermic reactions in your body. So just the idea of digesting food, which is basically combustion, right? But like broken up into lots of steps. It's releasing energy, and your body's then using that energy to synthesize new macromolecules and to do things. If you've ever had a cold pack that's like you snap it and it has a salt that dissolves and it gets cold, that is an endothermic reaction taking place, or physical process, the dissolution of the salt. And it absorbs energy from the surroundings, so it feels very cold to the touch because it's stealing literally your heat to make that reaction or process take place. And so it'd be endothermic. All right, so we've got general reaction dynamics, collision theory. We have our reaction diagrams. We have rates will increase with temperature, concentration, or a catalyst. And then we have equilibrium, which is that there are reversible reactions. Most of them are. And we're going to write these with a double arrow going both directions. So like A plus B can form C plus D, but C plus D can form A plus B. And we have these reversible reactions. And the balance between how many reactions and products exist when the reaction stops changing is when it has reached equilibrium. And we can characterize that. Sometimes there's more reactants than products when equilibrium is reached, and sometimes there's more products than reactants. And we characterize it with K, which is our equilibrium constant. And it's the concentration of our our products over our reactants. And there's always these little exponents here, and these correspond to the coefficients. And so this characterizes, this is our equilibrium constant. So it characterizes the reactant and product concentrations at equilibrium. It's like a ratio. So that means that if K is less than 1, we have more of our reactants than products. And if K is larger than 1, we have more products. And if it's equal to 1, we have the same amount of reactants to products. And so we'll also, when something is at equilibrium, so at equilibrium, there's no change. Once something's there, we can still kind of mess with it. Like if a change occurs to the system will always respond to, or the system will always find its way back to equilibrium. And it'll do that by either having more reactants form products or more products form reactants. And so this we call Le Chatelier's principle. Le Chatelier's principle tells us how the system is going to change or shift to re-find that balance that's described by the equilibrium constant K. And so if we, in general, like this is me summarizing these rules, if we increase the concentration of a reactant or a product, here, let's actually do it like this. If we increase concentration, then the equilibrium will shift to the opposite of whatever increased, to the opposite side. Please. And if it decreases, equilibrium will shift towards that decrease. And so that's really going to mean shifting to the product side to the right means that you form more products and decrease the amount of reactants to reach equilibrium. And shifting towards the reactant side means you form more reactants and decrease the amount of products to reach equilibrium again. So you can do this with concentration. We'll go over concentration. You can also do it with temperature. But the effect of temperature increasing and decreasing depends on if the reaction is exothermic or endothermic. And we'll go over that in lab this week and show some examples. But this is our week in a nutshell. Good luck with it. And let me know if you run into any questions as you're watching the lectures or working on the homework.